All right, recording is rolling. So it is Friday, October 21st. We're going to jump straight into the Kahoot. Overplaying a little bit. It's going to be a tight fit, but there's just some stuff I want to finish up with this section before we move on to the next section. So a bunch of guys just turned in your homework. Thank you for doing that. You guys remember your next take-home quiz is due on Monday. I gave it to you guys yesterday. Was anybody here not here yesterday needs a take-home quiz? Okay, so you guys got that? Okay. All right, and then you take on quiz. Right, and then thank you. No, I'm not hating. All right, so this Kahoot is on this formula right here. Force gravity is G-mm over r squared. So this is a good review for, hey, maybe a couple of quiz questions could definitely help you out on. Most of these questions are related to the inverse square law. There's a couple of oddballs in here, but most of them are. Okay. All right, and here we go. I was just about to. All right, I'll walk you guys through these. Suppose you double the distance. That's what that means, right? If you double the distance between two objects, what happens to the force? Double the distance. All right, so if you throw a factor of 2 on that r, which is the distance, and you square that factor of 2, guys, what's 2 squared? 4, and it's 1 over that, right? 1 over 4. Right? Bam, 1 over 4. Right? Obviously, objects getting further away. If objects getting further away from each other, isn't the force of gravity getting weaker? Right, less and less pull. Right, so 1 over 2 squared is 1/4. 1/4 of the force. Right, Gavin, Royal, and Cody, points on the board. Suppose you do the exact opposite. You cut the distance in half. They're getting closer together. Isn't this the exact opposite of the last question? Guys, what's 1/2 squared? What's half of a half? 1/4. What's 1 divided by a 4? 4 times? You say 4 times? All right, 4 times the force, right? Because they're getting closer together. Inverse square law kicks in. All right, points. Suppose you double one of the masses. Double that mass. Now what happens to the force? All else equal, of course. It's a factor of 2 on that mass. So the overall force also doubles. All right. Good. Now that one is a direct relationship, right? Double one of the masses, the overall force also doubles force of gravity. All right, Cody on fire, moving up. Gavin and still in the lead. Suppose you tripled both of the masses. Triple. Factor of 3, factor of 3. What is triple? Yeah, 9 times. 9 times the gravity force, right? So 3 times, right? Suppose, okay, now we're back to distance. You quadruple the distance. So 4 times the distance. And what is 1 over a factor of 4 squared? 1 over 4 squared is 1/16. You get 1/16 of the force. All right, you guys getting this? 1/16 of the force. Suppose you do the exact opposite. Now you have 1/4 of the distance. Now they're getting really close together. What is 1/4 of a fourth? Like if you have 1/4 of a pizza, and then you have 1/4 of that 1/4 of a pizza, don't you have like a 1/16 of a pizza? Right? And no, it's inverse, so it's 1 over that. What's 1 over 1/16? That's 16 times the force, right? 1/4 of the distance is 16 times the force. Suppose you cut the distance into 1/3. What happens to the force? What's 1/3 squared? 1/9. Right? What's 1 divided by a 9? get 9 times the force, right? If they're getting close together, the force is going up, right? Suppose you triple the distance. Now they're getting further apart. Hello, Mr. Griffin. Yep, I'm going down. Yes, probably.
Or I'm left there too.
Yeah, yeah. Okay, you guys okay with that? All right. So 1/3 squared is 1/9. Okay. These last 2 questions, let's actually calculate some forces.
C figure.
So suppose you weigh 500 newtons on Earth. That's your Earth weight, 500 newtons, right? And now we're going to a new planet that has the same mass but half the radial size. So it's like we've taken Earth and just like crunched it down, right?
Oh, gee.
Okay. So same mass but half the radial size. Okay. Now what's your new weight? Okay. Here, I'll walk you guys through this one too. So you can do the same formulas we've been doing all along, right? It's mathematically the same, right? It's like it's kind of like your distance to the mass of the Earth is like big cut in half. You can think of it that way. Okay. So if you have half the radial size, guess what's 1/2 squared? 1/4. Half of a half is a fourth. Now it's 1 over that. So guess what's 1 divided by a fourth? 4 times. Okay. So isn't your weight going to go by a factor of 4? And if your original weight was 500 newtons, what's 4 times 500 newtons? Right? You guys got that? All right, 2,000 newtons, right? So here you go. Same mass, smaller size planet. Your weight would go up. All right, for the win, for the win. Suppose you weigh 900 newtons on Earth. Okay. Now we're going to go to a planet of this, okay, same mass, but 3 times Earth's radius. So it's a giant puff planet. Okay, so same mass, but we just made it really big. So it makes big puff planet. Okay. So from a physics point of view, it's kind of like you tripled your distance from the Earth, sort of, right? Because triple the radial size, center to center. Okay. Okay. So we're going to throw a factor of 3 on that r, that distance r. Okay. Guys, what is 3 squared? 9. Okay. And this would be like 1/9. So it's a 1/9 factor. So your weight changes 1/9 of what it used to be. What is 1/9 of 900 newtons? Is it 100 newtons? You guys think? All right, let's check this out. Yeah, 100 newtons. To the podium with the bronze, Royal, with the silver, Cody, and the gold, 10 out of 10. Mr. Gavin. And we got some runners up, Nate and Pam. All right, nice job, guys. Nice job. All right, so inverse square law. I think it's a pretty good review. And hopefully helps you out on a couple of those quiz questions, at least. All right, so agenda here. All right, guys, turn your homework. Thanks for doing that. You guys got your take-home quizzes yesterday, so have this done by Monday. Right, so there's some stuff I want to finish related to like rotational motion, and then something else I want to fill in. Kind of related to gravity. So, all right, one thing at a time here. All right, so let me talk about. We'll talk about playing music. You know. You guys probably have some CDs around the house. Right, these are digital, but let's go back in time. If you go back to like 1970s, they had these big old records, like these analog records, sometimes called LPs, like long plays. Right? And this is based on technology. The technology that precedes this actually goes back to Thomas Edison. So the origin of this is they would have these like wax cylinders, which is a different shape I didn't draw here, wax cylinders, and they had a needle. Right? And then they would pipe in a sound and the needle would vibrate. Right? And as the wax cylinder would move around, create like a groove. Right? Then the wax cylinder would dry, harden. Right? And then if you run the needle back over those grooves, like, right? And amplify the sound, you can get the original sound back. Right? So update that technology, you can get this. 1970s, you guys got this. Right? Now, what does this have to do with like rotational motion? Well, this thing would rotate and there's a needle. It starts out on the outside edge, and as this thing rotates, it moves towards the inside edge, right? And it hits all these grooves, amplifies the sound, you get sound back. Right? Now, probably the easiest way to put this together, and what they did was they just had this rotate at a constant angular velocity, right? So it did the same turns per time, right? But hang on a minute, if that needle, here's my needle right here, is moving towards the center over as the disc plays, right? Doesn't the radial size change? If the radial size changes for a constant angular velocity, then the interesting consequence is that the linear speed between the needle, like the head of the needle and the surface of the disc, actually changes. It's variable throughout the plane of the disc. Right? Because here, if the needle's on the outside, one rotation covers a huge circumference, right? But by the time it gets to the last track, the one rotation is only a tiny circumference, right? In the same amount of time, right? Because, right? So that means that the linear speed between the needle and the disc starts out really fast. So starts out with a fast speed for the first track, and then it gets really relatively slower for the inside tracks that are later on. Right. All right. So that's go back analog a few decades ago. Right. Then fast forward a bit to the digital version, compact discs, CDs. So we're gonna swap out. We're gonna replace the needle with a laser. Right. Also, now this laser is just reading bits of data like ones and zeros, right? Like 0, 1, 1, 1, 0, 0, 0, 1, 0. Also, it does read from inside to outside. That's kind of a trivial difference between these two technologies too, right? And if you're just reading bits like zeros and ones and turning that into a sound file, then if you want to like pack as much data as you can on the disk, you guys see how maybe I have like 10 bits of data here that takes up like this much angular size, right? But the same 10 bits only takes up a very small angular displacement by the time you get to the last track on the outside. Right? Is it? So if your laser is like reading, same bits per unit time, that's kind of like having a constant linear speed of the laser against the surface of the disk, right? But the interesting consequence there is that for that to happen, okay, and this is crazy engineering, is that you actually have to slow down the rate that the disk spins, right, as it goes from the first track to the last track. Because the inside track has to cover like 10 bits and like the disk has to turn like this far, which is like huge turn. But by the time it gets to the outside, the same amount of information, right, the disk doesn't have to turn very much. So it actually slows down its angular velocity. All right, so that's fun. Food for thought. You guys think about that. Okay. Oh, what else I have to hit is Coriolis and hurricanes. So let me switch my screen over. I bet a lot of you guys know some about this, but gonna give you guys my Griffin version of this. Okay, so if you look at hurricanes, hey, look, this one here. Hey, do you guys see like a counterclockwise type motion? Counterclockwise, right? So hey, this one also has a counterclockwise type motion. Ooh, this is a famous one called Katrina from 2005. Hey, it's like counterclockwise. Huh. I wonder why do hurricanes form at all, and why are they always counterclockwise, the ones that come across Florida? Well, let's get this video rolling. Okay. So we're up in a helicopter. We're watching these kids pass around this yellow ball. You guys see that? We're up in a helicopter watching these kids pass around this yellow ball. Now, from our point of view, do you guys see that the ball only ever goes in a straight line? Like if I held a meter stick up to the screen, that's all it would ever do. It just goes in a straight line, right? Right, because of the law of inertia, right? Newton's first law of motion. But if you're on that rotating platform, this is what it looks like. Now, you guys know that ball is only going in a straight line, right? It looks like it's all going curvy because we're no longer in an inertial frame of reference. You're in a rotating frame of reference, right? So things get all wacky. That's called the Coriolis effect. Hey, is the Earth a giant rotating frame of reference? And if you had a big enough weather system, I bet this would probably also come into play and be consequential. So let's look at the entire Earth. Okay. Here's the Earth, equator, pole, other pole, something like this, right? Right. Now, so suppose we're up here with Santa Claus, and we got out our gift cannon, and we're just like firing presents out. Like, you get a present, you get a present. We're firing into the chimneys, you get that, right? Now, if the Earth isn't spinning, it just pretty much goes south, and yeah, in the story, right? Right. But that's not the end of the story because the Earth is rotating. The Earth is rotating like west to east. Right? You guys see the Earth spinning like west to east around this axis, right? Oh, so if you fire something straight south, right, the Earth is turning underneath it as it's going straight south. I mean, it's just going straight south is what it's doing, but the Earth is turning underneath it. So if you were on the surface of the Earth, wouldn't it look like then that this fired gift relative to the surface of the Earth is like curving off to the right, right? Huh, that would be like the Coriolis effect that you saw like with the kids on the merry-go-round, right? Same story, right? Now, what if you're down on the equator and you fire something straight north? People sort of figured this out. Well, there's one story according to lore that if you have a strong enough cannon or strong enough artillery, you start to wrench this effect. This might have been where people first realized this was going on. I don't know, I've seen. But everywhere on the Earth, no matter where you're standing, has the same angular velocity. And that angular velocity is 1 revolution every 24 hours. That's one way to quantify how fast the theater is spinning. 1 revolution every 24 hours. But depending on your latitude, you can have a different linear speed relative to the axis of the Earth, right? For example, if you're at the pole and the Earth turns, well, you haven't moved any distance relative to the Earth itself, so you have 0 meters per second up here, right? But the equator is going close to 1,000 miles an hour. Right? So if you change latitudes, you get different linear velocities. So same omega, different v, right? Okay, so now let's go back to the equator and let's fire something straight north. Again, if the Earth isn't spinning, it just goes straight north, no problem, right? Okay. But the fact that the Earth is spinning, this cannonball is coming from a place that had a huge eastward momentum, huge eastward velocity, and it's going into territory that where the ground just isn't moving as fast beneath it. So isn't this cannonball sort of like outpacing the ground beneath it as it's going north, right? Which will also make it kind of drift off to the right, relative to the surface of the Earth. So if you go south or you go north, right, then you're going to kind of tend to drift off to the right, right, regardless of which direction you go. You guys see that? Okay. That's the Coriolis effect. Do you guys think if you go to the southern hemisphere, that everything reverses and you kind of tend to drift off to the left? Do you guys think? Yeah. Let's you guys think about that. I bet you guys can figure that out, right? So it kind of reverses. Okay. All right. So now let's go off the coast of Africa. We're looking down on the ocean off the coast of Africa. It's really hot. The sun's beaming down. We've got all this evaporation, and it's leaving behind a low pressure, right? Right, low pressure because all that evaporation. So we're meteorologists. We're looking down on the maps and see a giant low pressure. Do you think all the air around it wants to fill the void of that low pressure? Do you guys think? I think so, right? Yeah. So just something like this, we got all these air masses moving in. But if these air masses are crossing significant latitude, they're also going to, relative to the surface of the Earth, kind of drift off to the right. If they all do that, you get a counterclockwise motion. And there you go. That right there, we're looking at a hurricane. Hurricane, right? All right. So again, trying to go through cleanup stuff I hadn't got a chance to do yet. Got that demo. Right. There's another really cool TED talk that I want to show you guys, which I'll do here, but let me sort this up. Now, part of this has to do with gravitation that we're talking about. And part of it actually is kind of a good segue to what we're doing next, which is energy. Right? Well, sort of in a way, I guess I get you thinking about this. Right? So there's really 2 topics he talks about, but it's on this one TED talk. By the way, this presenter is called, her name is Patricia Burchat. I just want to look this up, this TED talk she did. Right? All right, so there's a question. It's a very famous question that's floating around for hundreds of years. It's like, what is the ultimate fate of the universe? Right? So suppose I made a graph of what is the size of the universe as a function of time. Right? Now, if you go back about 150 years ago, so the most common assumption was that the size of the universe was static. Right? Although that immediately starts to not make any sense. If mass is gravitationally attract, then shouldn't the universe be like attracting on itself, sort of, right? So there were problems with that model, but people just used that as a running assumption until they got better data. They got better data about the 1920s. A guy named Edwin Hubble noticed that almost all galaxies relative to Earth are redshifted. You guys know what redshifting is?
Right? Yes.
Yeah, okay. So you guys ever stand by the sidewalk and you need a cell phone, right? Right. You guys ever stand by the sidewalk, car goes by, you hear meow. You guys hear that? Meow. Hear that pitch shift? You don't hear that if you're inside the car, but you hear it outside the car, right? Right. So if the car's headed towards you, like it has to go meow. Right. What's that called? That's called the Doppler effect, right? Doppler effect. Right. So so it has to do with like changing wavelength, like based on like frames of reference, right?
And like
No.
that too.
Yeah, light, exactly. Light can do the same thing. Now, light's a different type of wave, but it's also subject to the same idea.
It gets right if it moves away from you, moves toward you, right?
Exactly. And that's redshifting and blue shifting, right? So if I draw a wavelength of light, this is more of next semester stuff we'll get into too, right? You guys know all the colors of the rainbow are just different wavelengths of light, right? Like the longer ones are red, the shorter ones are like blue, right? Infrared, we can't see. Ultraviolet, we can't see. Roy G. Biv is all in the middle here. Okay. So yeah, like all the galaxies, except for like Andromeda and weird exceptions, are all like red shifted. In fact, some are more red shifted than others. So you can actually use this to figure out like how far away galaxies are and also how fast they're moving. And the further away they are, the faster they're moving. And this was all like clear evidence, some of the really good, solid evidence that that the universe is expanding, right? You can actually calculate it, apply numbers to it, right? Right, so red shifting. Right. So we know the universe is expanding, right? So let's go to let's say Griffin time when I was about middle school. A question that was around is, okay, well, what is the ultimate fate of the universe, right? So it was sort of narrowed down to a few possibilities. One really common thought was, well, maybe, oh, by the way, if you extrapolate this process backwards, it looks like everything is at the same place, same time, about 14 billion years ago. Okay, so 14 billion years ago, there's bam, big bang, universe expands, but everything gravitationally attracts. So maybe the universe is going to end in a big crunch. Right? That was one popular idea. Maybe we're going to end in a big crunch.
I think he does.
Now that's sort of analogous to if I take this, throw it straight up, comes straight back down. Right, that looks all like that. Right, but hey, could I take this, throw it up fast enough so it reaches the escape speed and just flies off forever? Okay, that's sort of like this. The universe is going to expand forever. Right, there is maybe a third possibility. Can I take this and throw it so it goes in orbit around the Earth? Okay, that's sort of analogous to, well, maybe it's technically possible that the universe like reaches an asymptotic size. Right, maybe it expands something like this. Right. Now, different teams of scientists set out to answer this question, which one of these three curves are we on? About 20, 25 years ago, so, right? And they all came to the same conclusion independently of each other. And what they got was none of the above. There was actually a fourth possibility that nobody was anticipating at all. Nobody had their eye on, was even thinking about it, even considering. But the data showed that there's actually none of the above answer. Now, this relates to not what we've done so far, but what this topic called dark energy. I'll let Patricia Burchett sort of explain this.
Like it's actually made more energy as it moves outward.
Exactly. Yeah, that is the answer right there. So let me actually draw what Royal said. Kind of for the video. I'm going to sort of spoil it. Sorry about that, but I guess that helps if you're watching this video at home. And Royal knew the answer anyway, which is maybe some of you guys did too. The universe turns out is actually expanding faster and faster. Now this has been observed to be the case. So this pink line is what we're actually doing. The universe is expanding faster, faster. Nobody knows why. This is a gap in our knowledge. That's why it's called dark. It's dark because it's dark to our knowledge. And it's energy because you can treat this as an energy term. But anyway, so I'm going to flip my screen over and we'll roll out the rest of the class. You guys can watch this really cool TED Talk. So yeah, sorry, a bit short on time today. I know it went kind of fast paced, but that's what we got. All right, and that will be the day.